All right, so good morning, everyone. So today is day 2 of rotational kinematics, and basically today, as you know, we're basically going to do some review, conceptual review, and as well as some mathematical problems that we're going to be doing, like from the AP workbook that I sent you guys on Google Classroom, as well as some Khan Academy questions and some quizzes as well. All right. So just to get started, um, this is our agenda. And before we get started for the practice problems, I just wanted to do a quick review, and we're going to watch a quick video as well. So just going back to the first day of what we learned, um, we basically have something called tangential speed and tangential velocity. So whenever we're talking about rotational motion, we talk about tangential and angular. So tangential is always um, perpendicular to the center. So the arrow of, either acceleration or speed or velocity is always perpendicular to the center at any point in the circle. And we use tangential because we have to have some sort of tangible quantity that we can use to describe motion in the linear pattern. But this um in this image to the left, right, you see the ball, it's moving in a circle, and um, that arrow is always pointing forward. And it's because we use this velocity at the instant. Like if we stop this image at one point in time, just like one frame, that object has an instantaneous velocity of going forward, and that forward direction is always perpendicular to the radius or the center of the circle. And we also use tangential speed to calculate period, things like that, and how how long does it take to travel from this point of the circle to another point of the circle, and we just do um, the arc length divided by the tangential velocity to get you your time. All right. So it's kind of like linear velocity, linear speed, but again, this is in a circle, so it's always perpendicular because the word tangent means perpendicular. Also in calculus, right? If you're calculating the derivative of a line, you're really calculating the tangent, the slope of the tangent line uh, at that very point that you're trying to calculate for. All right, so next we have tangential acceleration. In tangential acceleration is basically kind of like basically what we learned in dynamics with like change in velocity over time. This is basically change in tangential velocity over time. It's basically the same thing with linear. It's just that you're talking about moving in a circular pattern, so it's not linear. But we still use meters per second squared because it's arc length. Arc length is circumference, so circumference is basically 2 pi r. If your r is in meters, your 2 pi r is going to be in units of meters as well. And since your time doesn't change, time is always in seconds in this scenario, your units are also in meters per second squared. All right, so then we also talked about something called angular velocity, right? We have angular velocity and angular acceleration. Angular velocity is basically your change in theta. We talked about this quantity called a radian. A radian is basically your arc length divided by your radius. So it's a quantity that physicists as well as mathematics use. Also, if you do some coding, they will also ask you in terms of radians. It's basically a quantity that we use to measure the rotation across a circle. So let me just bring this up again. So let's say we have a circle that's like this, and we also have a circle that's like this. Obviously, the radius of the second circle is bigger than the radius of the first circle. However, if we were to measure um, the angle of this compared to the angle of this, your degree would be the same as well as your radians. However, your arc length would be different, right? Your arc length of the second one would be bigger than the arc length of the first one because the radius is larger for the second one. But that's why we use the term radian, because it's able to basically unify all circles and disregard radius. So it's kind of like a measure of how fast are you traveling in response to a circle. Because the reason why the radian does not change is, let's say if I draw a small circle, right, the same size circle inside of that small circle, right? Now you see that that is almost the same thing. The radian, the measure of degree does not change. It's always going to stay the same, you know, from here to here, from here to here. That degree is always the same. No matter if you extend that circle big, you know, or extend that circle small, it's always the same thing. Like even if I draw an angle right here, that radian is going to be equal to the first one. And that's why we use radians, because it's so easy to use, and also because we don't use degrees, because degrees is out of 360, and sometimes if you have revolutions, like if you're turning a tire, a car turns its tires like 300 revolutions in 1 minute, you're not going to be able to take 360 and multiply that by 300, and it's going to give you a really large number. So we use radians because we know that in a circle, there's the total is 2 pi radians, because half is 180, pi equals 180, and since a circle has 360 degrees, it's just pi times 2, so that's 2 pi. And that's your total radius. So if the problem tells you this car is having 2 revolutions, 3 revolutions, x revolutions, you just take 2 pi and you multiply it by those revolutions to give you the radian, the total number of radians. And using that total number of radians, you can now calculate your omega, which is your angular velocity. Basically that W looking sign, I believe is a Greek symbol, and you can therefore calculate angular velocity if you were given those values. And then using angular velocity, that leads us to our next thing, which is about angular acceleration. All right, so angular acceleration is almost like the same concept as acceleration, right? It's just like what it says, but it's towards, it's basically the change in angular velocity over time. It's not regular velocity, it's angular velocity. All right, so if we know that omega, right, is v over r, and we also know that it's the change in radians over time, right? Velocity is equal to change in displacement over time. Omega, or angular velocity, is basically change in radians over time, right? Or the displacement of your radians, how far you travel in that circle. We can also use the equation, right? V over r. Believe that will come up later as well, but those are some equations that are very helpful. Let's see. Right. This is equals V over R, right? And if we know that omega is those two equations, and we know that alpha, which is angular acceleration, is always the change in omega over time, right? Right, acceleration is always change in velocity over time. So angular acceleration, even though it's angular, it's still acceleration. It's the change in angular velocity over time. Now, if we're doing something like a change in alpha over a change in angular velocity over the change in time, we can simplify that as WF, or omega F, minus omega initial, which is basically your final angular velocity, minus your initial. It kind of like finding displacement. Like for displacement, you do your final position minus your initial position. This is basically the same thing, except it's the change in angular velocity. Now, after you get that equation, you can now simplify it and you get to delta W over delta T, which is basically what we had before. And later, you'll also see another derivation that gives you the equation V squared over R for alpha, and that's also very important as well. All right, let's move on. So we also talked about rotational kinematics. Rotational kinematics is basically your kinematic equations, but they're turned into rotational form. So instead of having velocity, you have omega. Let's write this down as well. So this is the conversion chart if you wanted to just memorize the, so basically if you just memorize the kinematic equations, you'll memorize all the rotational kinematic equations, because they are basically the same format. It's just you change some variables. So we know in translational motion or linear motion, we have velocity as v. But in rotational motion, we have angular velocity. So that's, I'm just going to put w, but basically omega. All right. Now, in translational motion, you also have acceleration, right? Because you have change in velocity. But because we're in rotational motion, we're not talking about linear velocity. And so what do you think is the variable that we should put for acceleration?
Angular acceleration?
Exactly. And what's the symbol for that?
It's not, wait, it's not A, it's like W.
Yeah, okay, it's called alpha. All right. So
Oh,
I know,
alpha, yeah.
yeah. And the W is omega. All right. So if someone says that in the future, you should know, like, you know, A is alpha. It looks like an A, but it's not. It's like an inverse U, but like intersected U. All right. And then we also have X, right? Displacement. We use delta X, right? Sometimes you see the equation as delta X equals V naught T plus 1/2 AT squared. In this scenario, they kind of like broken it down for you to be more specific. But for delta X, it's displacement, right? But what do you think should be the term for delta X in a rotational kinematic equation? All right.
Okay.
Yeah, go ahead.
It shows like the radians that change. I'm
Yeah.
not
So
really sure.
what should be the symbol?
Um, it's just theta.
What should be
Or
what should be in front of theta?
oh, change like delta.
Exactly. So, right, in in translational motion, we have delta x, right? But in translational motion, we have delta theta, right? And be careful, theta is always in radians. It's never going to be in degrees. Even if they give you degrees, you need to translate that into radians. All right, so that's basically it. If you see the equations, they just run on these three variables. And time is the same, right? You can't change the unit of time. Time is just seconds, unless you're talking about light years, or even light years is in seconds as well. So everything's in seconds. All right. So let's move on. Also, before I wanted to start with the review, I just kind of wanted to talk about graphs, because graphs are kind of very important. So let's make some graphs. All right, so right here we have, let's make 3. Right, and then let's make here a small, make this a different color. And here. All right, and then let's have graph like this. And then we also have for the red part, this, and like this. All right, and this is, let's start off with easy. Let's do displacement. So let's have this as displacement, and let's have this as time. So when you're making a graph, you need to include units, but for the sake of time, I'm just going to write in the variables. All right. So this is velocity, and this is time. This is time as well, and this is acceleration. All right. And let's move this over. Let's call this translational motion. All right, and then let's call this rotational motion.
Wait, sorry, I'm kind of confused. Wait, how are we looking at the graphs? Because like doesn't time go like in the x-axis? Or
So what part of the graph are you kind of confused on?
Or like this is like basically okay, because I thought like the time went in the x-axis. I don't know, or like
Oh yeah. I'm sorry. Yeah, it should be that. Sorry, I had a brain confusion. Let me just move this, shift this over. Yep, that is correct. Yeah, you can't have negative time. This is what happens when you wake up and then you have no idea what you're doing. All right, so yeah, that's correct. All right, thank you. So basically the same thing applies when you're doing. Let's move this over to copy and paste. And we also turn here. And again, you should always put units, but just because I'm kind of short on time, we're going to keep it as is. All right, so for displacement, what is the rotational equivalent of displacement?
is it like theta in time?
Yeah, so we use delta theta, or basically change in radians. And then we also have, so what's the rotational equivalent of velocity?
Omega in time.
Yeah, omega, or we just say angular velocity. And then what's the rotational equivalent of acceleration in the rotational form?
It's alpha or angular acceleration in time.
Yeah, exactly. So angular acceleration. All right, so let's say, let's draw out this scenario. Let's say we have a box and you apply a force to it. So it starts off from rest. Let's write this out as well. Starts off from rest. Okay. And then let's say it's in a shipping company, right? So the shipping company has those trailers that push those boxes forward. So let's say those trailers, right, apply a force of X newtons. Right? And then we want to describe the behavior of this box. And this is, they apply a force of X newtons at time t, right? And we basically want to find out what is happening to this box. We want to describe its behavior. All right, so the same thing, we're just going to do this first for a linear translational motion. And later, we're going to do one for rotational motion. So let's say it starts being applied a force of F newtons. Fx. Meaning when we subscript with x, we're talking about the force of x, and x is the variable of the number of newtons. All right, so and then let's make this time t. Let's make this start off right here. This is t. This is t. And this is t as well. And we're assuming that this line is the same for all parts of it. And let's erase this. All right, so how would you start off with displacement? What would you draw?
Well, if the box is accelerating, then it will be like a curve.
Exactly. But what would it look like in terms of the x variable? So let's make this. Let's say this is 0 seconds, right? This is the origin. It says that it applies a force of x newtons at time t. So how would you draw this graph?
So it'll be increasing like slope upwards.
At what? At 0 or at time t?
So it was at rest and then started increasing. So from 0, it starts at 0, but then as it moves towards 1, it starts going up. I think.
All right, so this is tricky. All right, so it says that it applies a force at time t, meaning from 0 to time t, it's at rest
Okay.
because no force was applied. So how do you think I should draw this now?
Okay, so like you don't draw anything from 0 to 1. Like I guess it's not moving, and then you start from 1 and then go upwards.
Exactly. So the exponential curve should look something like this. It should go up after time t because it was not applied at 0 seconds. Same thing. How would you draw the velocity graph then?
So it's gonna look kind of weird, but like basically from 0 to 1, like you don't draw anything, and then like you start like you draw like a increasing like line, like constant upward slope.
Yeah, okay, yeah. Constant slope. That's important. So how would you draw your acceleration now?
So acceleration would just be like a straight like line. Like I don't know what value to like it anyway. But also like 0 to 1 has nothing.
Yeah, exactly. So this is like a basic graph of displacement and velocity and acceleration, right? Later in the year, you'll have more difficult problems. Like let's say they apply a force at time t, and then they apply a negative force of y newtons at time t sub 1. So they can always add things, and that's kind of important in your graph that you show at that time t, or that variable at x equals your variable, that y is doing this behavior, y is doing that. That's really important. So the same thing if we're going to do that for a rotational form, right? Let's say we have a circle, a disk, and this is the center, right? And someone starts applying a force, actually a torque. All right, so we're going to talk about torque next time, but basically torque is the rotational equivalent of force in translational motion. So let's say someone applies a torque, right? Let's call this, just to know that as T. And they apply that force at time T equals 0. So let's make this. Applies a force at time T equals 0. And then at time t equals t, they stop applying that. Actually, we can just call that force at time r away from the center. All right, so we can actually call this force, because torque is what you get out of force times r. So this is just force. All right, so basically what's happening is that you apply a force, right, to this disk, and let's assume that the center is stationary, so it's not moving. It's like being hooked up to a pole, right, like a disk, also like a wheel, right? Cars' wheels are stick to an axle, so the center does not move, and you apply a force at time t equals 0. So 0 is at the origin. All right. Let's see if I can annotate. Yeah. So t equals 0, and then at time t equals t, they stop applying that torque. So meaning they stop applying the force. So how do you think this graph should look like? Let's make this 0.
Okay, so I think this time we now start like we actually start at the origin and we increase, and then like at t, it just like does it just like stop, or like does it go like I'm not quite sure because it's like just stop applying the force.
Yeah. So let's start off with your first part, right? Let's say this is all 0 at the origin. How would your delta theta look like?
I'm going to guess. Well, I'm going to like maybe I'm thinking like it's similar to like the first one where it's like curving up.
Okay. So be specific though. Like am I curving up for the infinity of time, like all the way to x going to infinity, or is there like a variable that I stop going exponential?
That's a good question. I'm not really sure.
Okay. So no problem. All right. So basically, from 0 to time t, right? It tells you it applies a force of time, starting from time equals 0. So it applies that force all the way to time equals t, because then after time equals t, it stops. So we would actually draw an exponential curve, right? Kind of like what you said, but it does not go all the way to it doesn't go past time equals t. It's like an asymptote. It's the y asymptote is when x equals t. So it doesn't go like after time equals t. It doesn't pass that boundary. All right. So what would you and then at the end the delta theta, after it goes after delta theta, it will just become like this. It will look something like this. Because after it transitions from when acceleration is changing, your delta theta is basically exponential looking. And then, but after you stop applying a force, there's no acceleration. But that doesn't mean that you don't move. It just means that there's no change in velocity. So if you are assuming a constant angular velocity, your graph would actually look like a constant slope because it's increasing steadily. So how would you draw your angular velocity graph then?
So for angular velocity, it's going to from the origin. It's going to start at the origin and just like increase at a constant like velocity until it reaches t, and then it will stop.
So
And
you just don't draw anything after that?
you draw like a horizontal line.
Exactly. Yeah, you're correct. So basically, you know what Anna said, you know, angular velocity, right? If you have no acceleration, it's constant. And it's basically the slope of velocity. So basically, all of these three graphs come from the one before, right? For delta theta, the slope of that is your angular velocity. The slope of your angular velocity is your angular acceleration. It's all this. And then you could take area, you know, area underneath a angular acceleration, area under a acceleration versus time curve is your change in velocity, right? Area under a velocity versus time curve gives you your displacement. And then I don't think there's anything else for data because there's no like value that we use to that's connected after data. So those two are really important. It's kind of like also if you take physics C, you're basically going to have differential acceleration. So you need to basically take an integral of your area underneath your curve, and they'll give you like a limit. So like from here to here, or like an interval, specified interval. And using the integral, you can calculate area such as like um, the change in velocity over time or the displacement over time. And that's really important. So right now what we're dealing with is kind of like a um, easy situation since they're all like linear, like straight lines. Like for instance, angular velocity, this looks like a triangle, right? So I can actually calculate this area just by doing 1/2 base times height, right? And this looks like a rectangle. So I could do that as well. I could just do length times width. But let's say you have a scenario like this, delta theta. This is exponential. How are you going to calculate the area of that? So that is something that you would need to use calculus for. And again, that's for physics C, but you know, for you guys who are really interested in doing that, you could look into like integrals and derivatives. All right. So last graph, what would you do for angular acceleration?
Okay, so you do like the straight line starting from like some point along the y-axis, and
Mm-hmm.
for afterwards, I think is it just like nothing, or I'm not sure.
Okay, so you basically got it. So angular acceleration graphs look kind of weird because it's like once you don't apply a force, there's no acceleration. So it actually does something like this. It just drops and then just stays at time t. It just stays at 0 for basically eternity, unless there's another force applied. And it does like this sudden drop. Like if you see that vertical drop, that's basically saying like it just stops accelerating. Like once you don't apply a force, it just doesn't receive any more acceleration. There's no like time delay or anything. It's just sudden. Same thing. You could even have a scenario where at time t you apply a force in the opposite direction, and you would actually have a graph looking something like this. It would go below the x-axis, and then it would go um, negative like this. So you could also have a scenario like this, but the first one is correct. All right. So I hope you guys kind of learned a little about, got some review. And now we're just gonna do some practice problems as well as watching some videos. All right, so and then we also talked about centripetal force, right? Centripetal force is basically a force that you receive when you, or occurs when you travel in a circle. So like for racetracks, for racing cars, they actually have, the stadium is built so that everything leans towards the center. Like if you go towards the boundaries, it's higher than the center. The reason why is because they want to build that centripetal force for the cars, so that the cars don't just slip out of the arena, that they stay in that track. And basically, it's because of centripetal force. Centripetal force is not something that you can see, just like other forces. I mean, like gravity, right? If you apply a force, like a physical force, you can see that, right? You're pushing something. But centripetal force is something that's imaginary. It's like invisible to the. I mean, yeah, it's invisible. Like you can't see it, but it still occurs. And physicists use that to describe why certain objects can stay in orbit. How planets can stay in orbit to the sun, how they can stay in the solar system. And how like roller coasters can stay also in that circle as well, and also how you swing things. That's all centripetal force. Um, Basically, centripetal force, we use the equation mv squared over r. Let me write that out as well. mv squared over r. M is your mass, v is your velocity, your tangential velocity, squared over r. That gives you centripetal force, and we use that as F sub c. And F sub c is usually your net force, because usually objects don't have a tangential acceleration, so they're only forced, according to Newton's second law, right? If you do a net force equation, your net force is your centripetal force, because it's basically pulling, like, basically why we have centripetal force is that if you don't have a centripetal force, your planet, or let's say you're talking about solar system, right? The Earth and Sun, how like the sun's gravitational field pulls in the Earth. The sun's gravitational force is the centripetal force, but it's like pulling in the Earth. So if you didn't have a centripetal force, your Earth would just fly away from the sun, because there's no force that's keeping it in a circular motion. And basically, why we have a force is that force equals mass times acceleration. So if your force and acceleration are both vectors, meaning they also consider direction. So if your velocity is perpendicular to to the center, what your force is going to do is that it's going to tilt that velocity direction inwards. So let's say at this time, it's going to make this at here. And then right here, it's going to make this like right here. And right here, it's going to tilt it like this. So every instant in time, it's keep on tilting your velocity, because you have, right, centripetal force gives you acceleration. Meaning if your centripetal force was towards the center, you would also have an acceleration towards the center. And we call this centripetal acceleration, A sub C. And that's basically, like if your acceleration is toward the center, you have like a graph that looks, you have a diagram that looks something like this, right? Your velocity is in this direction, and your centripetal acceleration is perpendicular to that. So your acceleration is not going to necessarily change your velocity, but it's definitely going to change that direction. So every second is going to shift it like a clock. It's just keep on shifting it every like millisecond. That's why it can move in a ellipse. It's not necessarily like I'm holding something, by a line and I'm swinging it, and that tension force is pulling it in. It's more of like a centripetal force, that's pulling it in. I mean, obviously, you can also have like a tension, like a line connected to a rope, connected to a ball, and you swing it like in the first scenario. But there's always a centripetal force. Centripetal force is always like the net force towards the center when we talk about um, rotational motion. All right, so let's move on to the next. So this again brings us to a quick derivation. So we're going to use some geometry. So basically, we know that theta equals S over R, right, is your arc length divided by your radius, or that distance that you travel. So the first scenario, we can draw a v1 that's going up because it's perpendicular to r. Remember, whenever you're talking about tangential speed or tangential velocity, it's always perpendicular to your radius. So if you can see, let's annotate on this, use a different color. So if we look at this, at this very time, your r is perpendicular to your v, right? And then right here, your r is also perpendicular to your v, right? Nothing new. And basically what we can now do is, because they share the same side called radius, and because their velocity vector is also the same, right? There's no acceleration, no tangential acceleration. The velocity is constant, it's just changing direction. We can then say that they're similar triangles. So if you do S over R, basically this is isosceles, right? R and R is the same. If you do S over R, that is the same thing as doing your delta V over V. And this is assuming, again, that V1 and V2 may not necessarily be the same, even though usually in most scenarios they are the same. So we can then draw this graph. Right, let's draw this out. Different color. And we're keeping the same direction of velocity. We're just rearranging the structures so that they're in the same direction. Like if you look at V2, that's the same thing as in the first diagram, but on the top, right? And the V1 is the same thing in the same direction, but shifted on the bottom. So we're just using the same thing, but we're shifting it down to make a triangle. All right. We're not changing anything. We're just borrowing it from different parts. So we would have V1 here. And then right here, we would have V2. And obviously we would have a theta as well. And the reason why we can assume this relationship that they share the same theta is because they share the same side before. Remember, like in the first diagram, you have R, and S is isosceles. And because V1 and V2 both share the same R value from the center, we can then assume the same triangle, that they would have the same theta, right? And also using vector addition, we know that if you have a velocity, if you have v2 going this way and v1 going this way, you must have like a net change in velocity, right? It's v1 plus v2, like the x and y directions, right? And that would give us delta v. And then basically after we have this equation, we can then say that s equals v times t. Basically we're saying the arc length is your tangential velocity times your time. It makes sense conceptually, even if you don't look at the diagram. Like if you're talking about running in a track, right? But your track is not like an ellipse, like a realistic track. In high school tracks, it's pretty like elongated circle. It's not really like a perfect circle. But if you assume that you're running in a perfect circle, right, your arc length is always your velocity times your time. I mean, even if it's an elongated circle, it's still the same thing. Distance equals velocity times time. It's just that what we're talking about is your arc length. Arc length is the same as distance. Now, if you do that, okay, so if you do s equals v times t, you can then say that, delta v over delta t is your acceleration, right? But because of this relationship, this triangle that we just drew, and also because we just assumed this relationship s equals v over t, we can then substitute s as v over t. Oh my goodness. We can then substitute v times delta t. Okay, so let me see how I can explain this one. So your acceleration is your change in velocity over time, right? Let me explain. But your velocity is basically s over delta t. All right. I think I'm not a really good explainer, but if you think about it in a sense, linear acceleration and rotational acceleration are related, and you can convert it using radius. Whenever you're talking about an angular quantity, you can always, do something with radius and you would make it into an angular equation from a linear equation. It's always with a radius variable. I'm really bad at explaining this, I'm sorry, but I'll find a video that I can show you guys and just post it on Google Classroom that I could give you a better explanation. I know we're kind of like short on time, so I don't want to leave this equation, so I'm definitely going to show you guys like a video next time, but just in a sense, it's always your R value, you know, like if you have a linear quantity, you can always do something with R and change it to acceleration. Like even if you have angular acceleration, angular acceleration is changing omega over time, right? If your omega is v over r, you're basically doing v over r times 1 over t. So if you have v over r times 1 over t, you're basically saying v over rt. V over rt is the same thing if you take out all right, so let me just show you this quick derivation. This one I remember. Okay, this one I remember. So we know that alpha equals omega over t, right? And alpha is then equal to v over, sorry, it should be like a v. It should be v over r, right? Times 1 over t. Because we're basically saying delta w is v over r. So v over r divided by t is keep, change, flip. So it's v over r times, right, change the symbol and then flip basically reciprocal of t. So then you would get this equation that alpha equals v over rt. Now we can do something with v over t. V over t is acceleration, linear acceleration. Therefore, we could say that this equals a over r. So it's your linear acceleration over your r value. This is the equation you would definitely need to know as well for future problems as well. All right, let's move on to the next problem. All right, so I kind of wanted to show you guys a quick video just to get some review. So let's see. Can you guys hear it or no?
Wait, how's the video started?
Yeah, let me share computer sound. Can you hear it? All right, let me start it first.
At this point, we've covered a lot of the basics when it comes to how things move, but we've mostly been focusing on only one type of motion, translational motion, which is when something moves through space but doesn't rotate. But rotational motion is also a thing, and an important one. For example, the spin of a football, both the soccer and the non-soccer kind, will affect the way it flies through the air. But the physics of rotational motion isn't all that different from the physics of translational motion. It still involves things like position, velocity, and acceleration. And many of the equations we use to describe rotational motion will look really familiar to you. But there are some important differences. Like instead of positions, there are angles. Instead of points along a line, you follow points along an arc. And there are times when rotational motion can explain things that sound impossible, but are actually true. Like when a point on a spinning wheel is actually standing still. So the rules here are the same. But rotational motion has what you might call its own circular logic. Of positions, there are angles. Inside of the disc, our starting point horizontally, and where is it vertically? Those axes make sense because we're usually tracking the object's motion along those directions. But for rotational motion, we really want to know the object's angle, what we call theta. Say we have a big disc with a dot painted on it. If we call the right side of the disc our starting point, then when the dot is at the right, its angle will be 0. And when the dot is at the left, its angle will be 180 degrees, half of a full circle. But even though we've been measuring angles using degrees until now, there's another unit that physicists use a lot. This will be the primary unit we use in this episode and the next. That unit is called the radian, and its name comes from the fact that it's based on the radius of a circle. If you think back to basic geometry, you'll recall that the circumference of a circle is just 2 times pi times a circle's radius. Radians describe angles by essentially telling you how much of that circumference is covered by a given angle. So 360 degrees, which is a full circle's worth of angles, would be be 2 pi radians. 180 degrees or half a circle's worth of angles would be pi radians. And to convert any number of degrees to radians, you just multiply the degrees times pi and divide by 180. So now we know how to describe the angle of something that's rotating. But what about the velocity of its rotation? Well, we've already learned that plain old translational or linear velocity is a measure of an object's change in position. And in the same way, rotational velocity is a measure of an object's change in angle. This is known as angular velocity and is represented by the lowercase Greek letter omega, which I want to point out looks a bit like a W, but isn't a W. And as you might have guessed by now, angular velocity is the derivative or the rate of change of angular displacement with respect to time. But we can also describe an object's rotation in terms of its tangential velocity. This is the same type of velocity we used when we talked about the physics of uniform circular motion. Remember, with the keys spinning around on a string and that vomit-causing carnival ride? In those cases, we described how when an object moves along a circular path, its velocity is perpendicular to the radius of the circle in the direction of the motion. And when you think about it, any rigid object rotating around a fixed axis is basically a set of points all moving around along circular paths. So at any given moment, each of those points will have a tangential velocity that depends on the path it moves through, specifically the radius of that path. In fact, its tangential velocity will be equal to its angular velocity times the radius. It's easy to see why this makes sense if you picture the spokes of a rotating wheel. All of the points along each spoke have to have the same angular velocity because they all cover the same angular distance in the same amount of time. But to get from, say, the right-hand side of the circle to the bottom, the points on the outside of the wheel will pass through a much bigger arc, covering more distance, basically, than the points on the inside. So the further that a point on the spoke is from the centre of the wheel, the greater its tangential velocity has to be. Like circular motion, rotational motion can also be periodic. Periodic being when the rotation repeats after a set amount of time, which is represented by capital T, also called the period. And the equations that describe periodic motion are pretty much the same as the ones we use for a single point that moves along a circular path. And so the frequency or number of rotations that happen every second is equal to 1 divided by the period. But frequency and angular velocity are really just two different ways of describing the same thing. They just use different units. Frequency is measured in rotations or revolutions per second, and angular velocity is measured in radians per second. And 1 revolution is equal to the circumference of the circle, 2 pi radians. So in order to convert from frequency to angular velocity, all you need to do is multiply the frequency by 2 pi. Now there's a special case when it comes to the velocity of rotating objects, and that's known as rolling without slipping. This kind of motion shows up in real life all the time. It's what happens to your car tires when you drive down the street as long as you aren't skidding, which let's hope of angular velocity. It's represented by the lowercase Greek letter alpha, and it describes how an object's angular velocity is changing over time. And as an object rotates, each point on it can actually accelerate in 2 different ways. Radial acceleration is another term for what we've been calling centripetal acceleration up until now. It's the acceleration inward of any point on our rotating object, and it's equal to the angular velocity squared times the radius. But there's also tangential acceleration, which describes whether an individual point on a rotating object is speeding up or slowing down. And like linear velocity, tangential acceleration depends on the distance between the point and the center of the object. More specifically, it's equal to the angular acceleration times the radius. So you see, angular position, velocity, and acceleration relate to each other in much the same way that linear position, velocity, and acceleration do. This allows us to talk about rotational motion with terms and equations that are familiar to us once we have the basics of translational motion under our belts. Next time, we'll see how the logic of rotational motion applies to another idea, momentum. For now, you learned about the qualities of rotational motion, including angular position, angular velocity, periodic motion, and the special case of rolling without slipping. We also talked about angular.
All right, great. So we have around like 5 minutes left. So Anna, what do you prefer doing? So we could do either quizzes, review questions, AP review questions, or we could do some, I believe, yeah, either quizzes, AP review questions, or if you have any homework problems you want to do as well. So what do you prefer doing?
Whichever one we can do on time, like which one would be like, I don't know, because honestly it's like mostly based on like how much time you have. So like whichever one, like.
All right.
Seems...
do you have any specific homework problem that you want to work on, or not? Or you got it?
I don't have questions right now.
All right, no problem. Okay, so what you guys are learning?
Oh, we are. We're finishing circular motion. I think we finished it, and we are just going to have a test soon.
Oh, you guys are finished uniform circular motion, right?
Yeah, down.
Okay. So this is kind of like basically a step further, but it's not that far from what you guys are doing. I think you guys gonna learn like energy or momentum next, and then afterwards.
Yeah. That's what my teacher said.
All right, great. So let's do. I think it will help you more if we do like an AP review question, because I think those are more important because you could like actually apply them. So let's. I'll share my screen. Let's do something. All right. Share screen. Move this over. 194. All right. So we have this problem right here. Page 194. If you want, you can also open up in your own book. It's a coin rests on a rotating turntable. Andrew collects the following data for the radius of the coin from the center radius, a distance the coin traveled in an arc, and the angle in degrees through which the coin rotated. And then part A, right? Remember from math class, that 2 pi radians equals 360 degrees. Use this fact to fill in the last column in the table. All right, so what would you, so this is kind of like simple, right? You know, degrees to radians. So how would you fill out the column to the right?
Yeah, I'm just trying to open the book. Can you give me like a second?
Yeah, no problem. Let me know. Let me know when you got it open.
Mitari, what was the page number?
Oh, it's 194. You can also look at my screen if you want and annotate on that if you want.
I got it now. Okay. So what was the question?
So just try to fill out the column to the right. Like how would you fill out the column to the right? Angle and radius.
Do I say it out loud or do I just fill it out and then like tell you?
You can tell me, or you can, if you want to annotate, you can also annotate onto this paper on Zoom, like with your with the text if you want. Do you know how to do that?
I'm checking. Like like when you draw. Is that what you're saying?
Yeah, like a view options on the top, and then you can annotate.
Okay. So for the first one, I'm just gonna say it actually. So to convert, since they gave us like the angle in degrees and they want radians, we can use that the formula to convert, and that would be like I think pi over 180 degrees. So would you get like 0.1 pi?
Let me just double check.
Sorry, it's because like my calculator doesn't work right now, so I'm like using my phone's calculator, and it's
Oh, no
weird.
problem. Yeah, you would get around like 0.35.
Yeah, that when you multiply times pi.
Yeah, all right. All right. So what would you get for a second one?
Okay, so that'll be 30 or 180 times pi. 0.52.
Okay. And next.
Okay, that would be 0.79, like rounded. And then for the next one, you will get 1.05.
0.05. Right.
And then you will get 1 point. Wait, did I put the wrong number? Okay. Okay, the next number will be 1.331. 31.
3-1. Okay.
And then 1.57.
Okay. Then
And then you'll get 2.09. Unless it's wrong.
yeah, so okay, so 360 degrees, if it's 360, it's always 2 pi. So we would have
Okay.
something around 2 times pi is around 6.23, 6.28. 190 degrees is just pi. So that's around
Yeah.
3.14.
Wait, I have a question. So like when they ask like the angle in radians, do we have to calculate or can we just leave it like in terms of pi?
You can leave in terms of pi. Like if they give you like a revolution and they want you to calculate the total angular distance travel, like the theta travel, you could leave it as 2 pi times the revolutions and leave it pi, and then you could convert it later. But depending on what the answer asks you, like if it says leave answer in terms of pi, then you leave it in terms of pi. If it's asking for like the exact value, then you would have to convert to a decimal. All right. So 120 times this should be around 2.09. It should be half of pi. So half of pi is 3.14 divided by 2, 1.57. Yeah, that's correct. All right, so everything else is correct. Okay, so let's move on to part B. What would you now use? Which trial numbers would you now use to graph?
I'm gonna guess like the nice numbers, like maybe like 60, 90, 360.
Okay,
Um,
try
um
look at. Okay, so let me give you a hint. It asks
okay.
you to create a graph of arc length versus angle in radians, right? So it's arc length versus angle in radians. Now, angle in degrees and angle in radians are two different variables, but because we converted them, either one you use will represent the other. Does that kind of make sense?
So
Like,
just yeah, so they're the same value basically, which is different.
yeah, it's just in different units. It's like saying what is velocity in meters per second, and they ask you to convert to feet per second. You know, it's the same value. It's just in different units. Now we have 4 different variables right here. We have radius, arc length, angle in degrees, and angle in radians. Now, since we already said that angle in degrees and angle in radians is almost the same thing, we don't need to worry about using one or the either. We could just use one. And we have
Oh,
radius and arc length. What do you think should be? What do you think? And it tells you they wanted to create a graph of arc length versus angle and radians. So they want. Let's start this off. They want this variable and this variable. But you have this variable right here as well.
okay. So
So what? Yeah. So what would you not use?
okay, I will choose 8, 7, 6, and 5.
A, 7, 6, and 5. No. Look at the radius
No.
meters. Look at the radius meters.
Wait, do you
see a
want them all
pattern.
to be the same, or do you want them to be different?
For radius?
Mm-hmm.
Yeah,
The
you
same?
want them to be the same.
Okay, okay. So 1, 2, 3, 4.
Just up to 4?
Okay, well you can use 5 of them.
Yeah, exactly. You want to use 1 to 5. The reason it was why is because whenever you're making a graph, you don't want to have 3 different variables. It's gonna make
Okay.
it's gonna make your graph faulty. So you have to always make sure you have 2 variables, an independent and a dependent. So in your trials, you'll just explain that because the radius is the same, therefore my graph would be correct. If you had like 6, 7, 8, the radius is changing, so you cannot assume the same arc length for all of them. You know what I'm saying? Like it would
Yeah,
have 3 variables. That's not you cannot use.
that's what you were saying about the leader in the large circle.
Yeah,
Sort of.
exactly. Like yeah, I mean your arc length is dependent on your radius. Right? Your larger your radius, the bigger your arc length. But in this scenario, they're not asking you about the relationship between radius and arc length. They're asking you to create a relationship between arc length and radians and angle. So you need to make sure everything else is constant, like a control variable. Okay. All right. We went like 5 minutes overboard, so I don't think we would have time to finish this problem. But we did do the beginning, so if you want to, you could do it like on your own, and I will also like next week if you want, or you can come to tutoring either this week and we can go over it together, or if you have
Okay.